Okay, good evening, and we are continuing with the study of the transistor. And in previous classes, we look at the BJT, basic junction transistor, from the NPN perspective. This is the NPN transistor. And we stated that the NPN transistor was basically two PN junction placed back to back, one in a forward bias direction and one in a reverse bias direction. Now we're looking at the PNP, which basically has a semiconductor material arranged in a PNP direction with respect to the NPN, which has a semiconductor material arranged in the NPN direction. Now we say now that in the PNP, the VEE and the VCC in reverse bias. The VEE and the VCC is in a reverse bias. But note in all cases, whether it be the NPN or the PNP, that electrons go from negative to positive, and current flows from positive to negative. This all the time. Electrons flow from negative to positive, and current flows from positive to negative. All right, so we're going to draw basically the PNP circuit. Well, current will be flowing in this direction, and electrons flow from negative to positive, current flow from positive to negative. The polarity of this is VCB, the collector base. VCC. RC, RE, emitter, collector, and we're dealing with PNP. Most the direction of the I base in the PNP, you have it coming down, in the NPN, we have it going up. I know also the emitter direction in the NPN is going in that direction, in the PNP it's coming into the base. Emitter. Going up. We said again that the PNP transistor has its bias voltage VEE and VCC reversed from those in the NPN. That is, VEE and VCC are in reverse bias. And this is necessary to forward bias the emitter base junction and reverse bias the collector base junction. And since emitter current is mainly due to holes moving from the emitter to the collector, the positive direction of the emitter current is into the emitter as shown, into the base as shown. All right. Note that the PNP circuit symbol, that the arrows point into the emitter to signify the direction of the positive emitter current, and the collector and the base current flows out of the transistor, and as before. I guess if you recall from our circuit diagram of the PNP, collector. So emitter was emitting, and collector was collecting with respect to the base. So the base. Now we know in the PNP now, we see now that the emitter is coming so. So that is in reverse bias, the BE and the BCC. All right, the equation still holds that IC is equal now to alpha IE plus ICO. Equation 1, and IB is equal to 1 minus alpha IE minus ICO. And if we let know that alpha IE is not much greater than ICO, then we could neglect the ICO, and we would say no that IB is approximately equal to beta I. And where beta now is equal to alpha over 1 minus alpha. And we know that this calculation, this factor, turns up so often in transistor calculation that this is giving the term beta. Now we also define a small signal amplification factor HFE as delta IC over delta IB. And that's equal now to beta plus delta over delta IB. The small signal current amplification factor HFE is therefore HFE is equal to beta plus delta beta over. And if you let a delta beta over delta IB times IB small compared with beta, then what we'll have now is that HFE will be approximately equal to beta, approximately equal to HFE. All right, let's draw the common emitter large and small signal circuit for the PNP. And we show HFE, and it's approximately equal to HFE, and approximately equal to beta, and beta is equal to alpha over 1 minus alpha. All right, let's, which one of these diagrams we should take out for the time being? Draw like that. Draw. You have the common emitter large and small signal current in, minus 6, 10 minus 5, 10 minus 4, 20 minus 2, 20 minus 2, 10 minus 1. Here are H, F, E. Now, beta equals H, F, E. This is in milliamps. And this is H, F, E. I know, so we say if we let delta B over delta IB, delta beta over delta I, yeah, IB small compared with beta, then HFE is approximately equal to beta, is approximately equal to HFE. And if we should draw the base, the basic transistor amplifier, the common emitter configuration. Let's do that. Let's take up some of these calculations. Note the calculations and the relationship between beta, HFE, and HFE. All the rest of the relations. We're drawing here now the basic transistor amplifier. then cosine over t. And this is the CE, or common emitter configuration. Okay, we know that typical operating range of 100 milliamps, the HFE is approximately equal to beta. And is relatively independent of changes in the collector current. Yeah, so we see that the property that HFE equal to beta plus delta V IV over delta IV is a property of the transistor itself. And yeah, it's a property of the transistor, and it does not depend on external circuitry. Now the assumption that beta is equal to HFE equal to a constant is often made to simplify the circuit analysis. Now for the common emitter configuration, for the C, we have known that IV is equal to VV plus VIN cos omega t minus VQ over R. And when this assumption has been made that the base emitter junction is operating in a linear range with respect to VBB, with respect to lithium magnesium. VIN, much greater than where the assumption has been made that the base emitter junction is operating in the linear range with VBB minus VIN much greater than VBEQ, and that is known as the RV, the factor equal to 0. Since linear operation with no distortion is assumed, IB will consist of both AC and a DC component, and in that case, IB will be given as, let's write this here. Where should I take off? IB will be given as IB is equal to the DC component is the AC component is so the DC component and the AC component collector current would be now IC. Now with similar interpretation for the DC and AC component, the small signal current amplification is then, let's get the amplification. Small signal amplification will be and this is independent of the circuit and is a property of the transistor. Are supposed to know that beta is equal to 20 and equals 5 cosine omega t. Then application cosine omega t equals h f equals beta equals 1. 20 and 5 plus I over 2 equals to 100 cos over 2. And this shows now that the output current is 20 times greater than the input current. And if we should look at a relationship between beta and alpha, let's try and look at the relationship between beta and alpha. Get some chalks here. Chalk is relationship between beta and alpha would be 0.95 alpha beta equals alpha over 1 minus alpha beta 0.19 So that's a relationship between beta and alpha. Beta being equal to alpha over 1 minus alpha. If alpha is equal to 0.95, beta is equal to 19. If alpha is equal to 0.98, equal to 49, 0.99. So small intervals of alpha really give you large intervals of beta according to this relationship. Because we're just increasing from 0.95 to 0.958, that is a factor of 0.03. And from 0.98 to 0.99, that is 0.95 to 0.98, that's 0.03, from 98 to 0.99. That's increasing. That's 0.01 interval, and to 0.995 to the 0.005 difference there. And these are the interval, the corresponding interval in beta. Okay, so you note that that in the nonlinear region of operation, we assume that this thing was linear, but in reality, there's a nonlinear portion here. And what we'll do, we'll use the Ebers-Malls or the Ebers-Malls equation to find the actual behavior, the exponential behavior of the nonlinear section of the curve. transistor characteristics. So really, this thing is not a straight line, but is an exponential curve. Ebermann's equation give us the descriptive exponentials for it.